Hi everybody. Today we are going to talk about continuous functions. Now the lecture today is probably going to go a little long, so we will probably break it into two parts. And since we do have a lot to do, let's get started right here, right away. So we'll start off by saying that everything we're going to do today is going to be with a function. It's arbitrary function, so it'll be functions f, whose domain is a set X, which will be a subset of RL, and the target space will be Rm. Now, in some of the examples that we'll do, the target space will actually be just R, so M will be 1, but we'll be doing things generally enough so that we can regard the target space as Rm in general. And so we have to start off with a definition of a continuous function. So we're defining what it means for a function to be continuous at a point x bar in the domain. So we say a function is continuous at the point x bar if every sequence, see, this is an implication. So it says if we have a sequence xn that converges to x bar, then it's got to be the case that the sequence of images under f of the xn's has to converge to f of x bar. In other words, for every sequence that converges in the domain, the corresponding sequence of points in the target space has to converge to f of the limit of the sequence in the domain. So that's our definition of continuity in terms of sequences. And what we're going to do today, among other things, is we're going to actually give altogether at least four, alternative equivalent definitions of a continuous function. Slightly different contexts, but altogether there will be several alternative equivalent definitions of a continuous function. And to give the first alternative to this definition, let's define the notion of the limit of a function. So let's come over here and we'll say definition, the limit as x goes to x bar of the function f is equal to an a, and notice that since the target space here is Rm, this a has to be in Rm because that's where the values of the function lie. And of course the x's are in RL. And by the way, I've used RL and Rm here just because I'm going to be using n, just like I did here, as the subscript that denotes which term in the sequence we're talking about. So we'll be writing sequences as xn's, and so I can't use n then for the dimension of the domain or the target space. So we say the limit is this point in Rm if for every epsilon greater than 0, there is a delta greater than 0, such that if the norm of x minus x bar is less than delta, then it's got to be the case that the norm of f of x minus a is less than epsilon. So let's do a couple of things here. First, let's note that we could write this implication, or the elements of the implication, in a slightly different way here. We could write that this is that if x is in the ball around x bar of radius delta, that implies that f of x is in the ball around A of radius epsilon. And we could also write this as if the distance between x and x bar is less than delta, then it's got to be the case that the distance between f of x and A is less than epsilon. So these are just two alternative different ways of writing the same thing, the implication part. And of course, this part has to go here and here too to make the whole statements equivalent. So all I'm writing here is an equivalence to this implication. And this is perhaps useful in the sense that it's a little more visual, a little more geometrical, because we explicitly are talking about the ball of radius delta or the ball of radius epsilon. And this is, of course, useful because it indicates that we could actually generalize this definition of this definition over here of continuity and our definition of limit, which is going to give us an alternative definition of continuity. We could generalize that to metric spaces in general. It don't have to be norm vector spaces or Euclidean space. Don't have to be finite dimensional. Again, we're not going to be redoing that in here, but it's useful to kind of recognize that because this is something that you'll be doing later on. So let's now come back over here and let's note that with this definition of the limit of a function, we now have this theorem that says that f is continuous at x bar, at the point x bar in the domain, if and only if the limit as x goes to x bar of f of x is f of x bar. In other words, if and only if this A here is actually f of x bar and not some other point in the target space. And so the theorem says f is continuous at x bar if and only if this condition is satisfied. So that means that the statement that the limit of f of x as x goes to x bar is f of x bar, that statement is an alternative definition of continuity, or to put another way, this theorem is a characterization theorem. It gives us an alternative characterization of continuous functions being continuous at a point in the domain. So we now have two equivalent, it says if and only if, two equivalent definitions of a continuous function at a point in the domain. So let's draw a picture of what's going on here. So let me do that down here. Perhaps I should have done that with the first definition. So let's do that over here. So let's suppose this is the set X, which is a subset of RL. That's supposed to be an L there. I'm not so good at writing down like this. And let's say this over here is the range, the image of f of x, which is a subset of Rm. Our function f goes from here over to here. And let's suppose that this is a typical point x bar over in the domain. And let's suppose that this is f of that x bar over here in the target space. Well, the first definition that we gave says that any sequence, so we'd have to check it for any sequence that converges to x bar in the domain, the corresponding images, so every one of these points in the domain has an image over here under f. F takes each of these points to a point over here, and of course that might look like this, and it's got to be the case that the sequence of images converges to f of x bar. That's what the first definition says, and maybe I will use a different color here. The new equivalent alternative definition says that we have to have the limit as x goes to x bar of f of x equal to f of x bar. And if we look at what that says in detail here, it says for any epsilon greater than 0, so that epsilon would be giving us an epsilon ball over in the target space. And for this, let me call this point for the moment, let's call that the point A in Rm. Of course, we're going to say, for continuity, it's got to be the case that f of x bar equals that point A. For now, just let that be A. And so this says that we have to be able to show for this epsilon neighborhood, let's even put a little thing on here that says the radius is epsilon. We have to be able to show for this epsilon neighborhood that we can find a neighborhood or a ball in the domain around x bar such that everything in that ball gets mapped into the ball over here. So that says we have to find a delta over here of some size, some delta over here, such that everything in the delta ball around x bar gets mapped into this epsilon ball around the point A. And if f is to be continuous, it's got to be the case that the A that is the limit is actually f of x bar. Now, it's kind of intuitively, I think, pretty clear that these two, I'll call them both definitions, even though the second one says theorem, but the fact that it's a characterization theorem really says it's an alternative definition. The fact that these two definitions, I think if you see what they say and you think about it a little, it's kind of clear that the two conditions say the same thing, but of course it has to be proved. And that the proof is pretty straightforward. I don't know if it's in the lecture notes, but if not, I'll probably give as an exercise because it's pretty easy and pretty straightforward to prove this theorem. And so I think that's all we need to say about this little diagram down here. Let's come back over here, and now let's give an example of, in fact, we'll give a couple of three examples that differ in sort of systematic ways of the definition in practice and what actually happens here. So let's say example here is going to be f of x, let's say, is 2 times x. Let's say x bar is 1, and let's say a is 2. So I'm just specifying the function, and I'm specifying what a is, and I'm specifying what x bar is for the purposes of the example. So what I need to do is say for any epsilon, I need to find a delta that will do what is over here on the right-hand side. So the way to find that delta is the way we go about it usually is pretty similar to the way we figured out the n bar that would put us far enough out in a sequence to guarantee that all the subsequent terms would be within epsilon of the point that we wanted to show as the limit of the sequence. So how we went about trying to find such an n bar, how far we had to be in the sequence to get within epsilon, we do pretty much the same kind of things to figure out for a given epsilon what delta will work for the purposes of establishing the limit of a function. Is what it is. That is to establish that we can get close enough to A. And so I'm not going to go through doing that here. I'm just going to say it's pretty straightforward. And here it becomes pretty obvious that what we want to do is say, let's let delta be always 1/2 epsilon. Okay, let's just see if that works. So if that's the case, then it's now we're going to have that that if x minus x bar, okay, now I left out one thing here. It was probably pretty obvious, although you might have noticed. I didn't think of it, and you might not have thought of it either. But it's clear here in this example that I'm not using any old RL and RM. This is a real function. That is, it's real valued, and the arguments are real numbers, so it's a real function. So the x's are in the reals, and the value of the function is in the reals. So in this example, L is 1, M is 1, okay? So, and since both L and M are 1, that I've got a real function, real numbers in the domain, real numbers for the values, the norm here and the norm here, they're both just absolute values. So I'm going to write absolute value instead of norm because they're real numbers. So if x minus x bar is less than delta, well, that's the same in this example now as saying that x minus 1, because x bar is 1, is less than 1/2 epsilon, because delta is 1/2 epsilon. But that's the same on the right-hand side as saying 2 times the absolute value of x minus 1 is less than epsilon, and that's the same as saying that the absolute value of 2x minus 2 is less than epsilon. And of course, 2x is f of x. 2 is a. So that's the same as saying the absolute value of f of x minus a is less than epsilon. And that's exactly what we need to show to establish that the limit of f of x as we go to x bar equals 1 is a equals 2. So we have for any epsilon, there is a delta, and it's that delta such that x minus x bar less than delta implies f of x minus a is less than epsilon. We have exactly this statement satisfied. So therefore, we have the limit as x goes to 1 of this f of x, of this function, is a, which is 2. And then let's finally notice that this also establishes that the function's continuous at x bar equals 1. Here we are here. The function's continuous at x bar equals 1 because a is f of x bar. So the limit of f of x is equal to f of x bar. So let's just say a is 2, which is f of x bar. So the limit as x goes to 1 of f of x is f of x bar. F is continuous at x bar equals 1. So that's just an example. So this is not a proof because, well, it's a proof, but it's a proof of a pretty limited statement. It says for this function, at this point, not at every point, at this point, the limit of the function at this point is 2. Now, of course, with this function, actually I didn't draw the function, so maybe I will actually draw a picture of the function down here because I think that's going to be useful as we move ahead. Let me see if I want to put that over here. Let's actually, yeah, I think that'll work. So let's put the diagram of this over here. So let's see if I can draw this without the x-axis starting to trail off like this. We can see that the graph of the function looks like this. I don't necessarily have the same scale on both axes here. So this is f of x equals 2x. Let's say that let's say that this is A. Let's say that this is x bar equals 1. And let's let this be epsilon here, A minus epsilon. And let's let this be, it's about, let's go over here first. And let's say that's about A plus epsilon. Ooh, that's not so good. So let's actually make that look a little bit better there. I didn't get that so that the two intervals don't look at all like they're the same size. So let me try to make that come out looking a little better. Let's let this go here. That's closer anyway. And this comes down here. So this is x bar plus delta. This is x bar minus delta. Let's even go out here like this. They make them look a little more like they're the same size here. So this is the distance epsilon, and this is the distance epsilon. And so we can see here that what's happening is that if we have an x that is within delta of x bar, that means we have an x that is somewhere in this interval down here. And the implication here is that the distance between f of x and a, here's a, f of x is however high the graph goes, that's going to be in here. So what we've actually shown is that for the epsilon that we're given, we choose our delta, and then we guarantee that if x is in this interval here within delta of x bar, then it will have to be the case that f of x is within epsilon of a. So that's a kind of a diagram what's going on here. And so let's now look at a second example. And for that, let's take off part of what we have over here so that we have space to do a second example.